Okay, so as you might know, we are not going through such nice days these days, especially these period, let's say, after the events in the killings in the east of Turkey where 30 people were killed. Now in the last weekend we had like 100 people killed in Ankara. But as you might also know, there's a strike going on. I just don't see the point in stopping the lessons. Eventually these days, this period will pass, that's what I hope at least, and when the period passes, we should be ready. So I will keep on, we will have the lecture today. Now, let's just first of all review what we had done last week. Now, if you remember, we were first discussing the measurement. The measurement was basically comparing various quantities. So if you are measuring the length, you are comparing a given length with 1 meter. And when we were defining the 1 meter, we were mainly comparing it with some light. And when we were measuring the time, we were comparing it with 1 second, and when we were defining the second, we were comparing it with the oscillations of a given radiation. Once we know how to measure things, we started to describe the position of objects. So first, as an example, we were looking at one-dimensional motion. Of course, the motion that we observe around us is not one-dimensional. It's rarely restricted to only a line. It will be making a complicated motion, but we will eventually come to that point. So if we restricted ourselves to the one-dimensional case where the object was moving only along a line, to describe its position, we first had to choose a reference point. So once we determine, okay, so let's say this is our line, our object is moving only along this line. So this is our reference point. And so we decided to call this direction the positive direction and the other direction was the negative direction. This choice is completely arbitrary. One of you might choose this direction to be the positive, the other one can choose the other direction to be positive. Physics the nature doesn't really care about which direction you choose. So once we chose that direction, the position of the object at this point, we said, okay, it is at plus 50 centimeters. If it was in, let's say, over here, it was, let's say, minus 50 centimeters. That's how we describe the position of object. There was one thing that we didn't mention, but you should pay attention to. Now, if you look at this object itself is something like 10 centimeters. So if it is here, now this point will be like 60 centimeters, this point will be like 50 centimeters, the position of this point. So when we talk about the position of such large objects, we have to also choose a point on the object itself. So if we have to choose a reference point, we have to choose a point on our object, let's say this point over here, and then the position will be determined by the location of that point on our object relative to our reference point. Now, another thing that we will be ignoring for the time being, or we will be restricting ourselves, would be if this object is something like rotating like this, we will also not study them until the second half of this semester. Eventually, we will describe this. The complete motion of this object can involve translation, that is the changes in its position, also just rotations like this. And they can be combined in complicated ways. And we will be studying all of these in the second half of this semester. And then we described, if the position is changing in time, we describe the average velocity, which was the change in, this is the displacement divided by delta t. This delta x is the displacement. We were discussing about an example where one of your friends was sitting in that chair, in that seat, and we had chosen this direction to be positive, the other one was negative. So if your friend moved from that chair to the front of the class, he had some positive average velocity. Now, when he moved from here to there, during this time interval, he had a negative average velocity, but throughout his motion, he had zero average velocity because his displacement, the total displacement was zero. Now, we also had an average speed. This is, let's say, L over delta t. Well, you can have various definitions of the average speed. L is a covered distance. So, for example, in the example of your friend, Although his average velocity when he moved here and then back was 0, his average speed was not 0 because he covered something like 10 meters in 6 seconds, so his average speed was 10 over 6. And we defined it, later on we defined the instantaneous velocity. Well, we will rarely write this instantaneous. Whenever we are talking about velocities, we will always mean instantaneous quantities. And this was defined as the limit as delta t goes to 0 of delta x over delta t, which is nothing but the derivative. This is the definition of the derivative. So if you know the position of your object is a function of time, just taking its derivative, you know the instantaneous velocity as a function of time. We also discussed how to do this, how to interpret this geometrically. So if we had, let's say, this is the x as a function of time, this is our time axis. So if this is the motion of our object, how these position changes as a function of time, the average velocity between time t0 and t1 was, okay, so we don't have power here. Elektrik yok da. Elektrik yok şeyde. 3 yolda. Elektrik gelmiyor. So the average velocity between time t0 and t1 was nothing but the slope of this line. Let's say this is theta. The average was tangent of theta. And the instantaneous velocity at time, let's say t0, was nothing but the slope of the tangent there. Okay, some more Greek letters. This is theta. And this is called phi. These are the letters that we generally use to denote the angles. So this was the geometrical interpretation. And now we discussed how do we go backwards. So if we have, in these examples, we are assuming that we know the position as a function of time. So how do we obtain the velocity? And we showed that if you know the velocity as a function of time, if you multiply it by a very small time interval, this is its displacement within this very small time interval of length dt prime. If you sum all the displacements from time t0 up to t1, you would obtain the change in the position, its displacement between these two times. Now, we didn't give a geometrical interpretation to this one, but we can also interpret this geometrically. Let's assume that you know the velocity as a function of time. Let's assume it has such a shape. And we can just divide it into very small time intervals. Now, we know that if the velocity is constant, then the average velocity is equal to that constant velocity, and the displacement in a given time interval will be v0 times delta t. This is valid only if the velocity is constant. Now, here the velocity changes in time, so we cannot use this result. But the trick we can do is we can just divide this interval. Let's say this is our t0, this is our t1. Divide this interval t0 to t1 into very small segments. And rather than study this continuous curve, we can just approximate that continuous curve by this broken curve. Now, this continuous curve and these broken curves, they are more or less the same. Now, of course, if you take the width of these time intervals to be smaller and smaller, the broken curve will be more and more similar to the continuous curve. Now, if this is the length of this time interval, here we have a rectangle. The height of this rectangle is the velocity at the time t prime. I say this is t prime. The height of this rectangle is v of t prime. The width is d of t prime. So this area over here is equal to v of t prime dt prime. Now, this is the distance that our object covers within this time interval dt prime. But it is also the area of this rectangle. Well, the area of the rectangle is nothing but the width times the height, so it's the area. So the distance covered by an object, if you know the velocity as a function of time, the distance covered by an object between t0 and t1 is nothing but the area between the velocity curve and the time axis. Now, of course, with the understanding that any area below the time axis should be taken as a negative area. It's basically the velocity is negative, so the area would be negative. That's, again, a convention. Now, do you have any questions up to here? Now, we will be going in more detail in the acceleration. Phi. Phi.
What? To explain that, I can understand the
blue line. Okay, so how we define the instantaneous velocity? This was, okay, so let's look at this triangle over here. This one. This is our angle theta also. Now, this height is our delta x, and this width is our delta t. And we had defined the average velocity as delta x over delta t, which is nothing but tangent theta. Okay, this is this expression over here. Now, this orange line is a line that crosses our curve at 2 points. Now, the instantaneous velocity, on the other hand, we had defined it as limit as delta x of delta x over delta t as delta t goes to 0. So that is, we have these 2 points. Now, our line crosses our curve at these 2 points. So we just take this point, let's say, and bring it closer and closer to this point. In this limit, delta t goes to 0. Of course, as we are moving this point, the orange curve is also changing. In this limit, the orange curve will be this blue, this orange line will be this blue line, and the blue line crosses our curve only at a single point. That is the definition of a tangent. And this phi is the slope of this, or the tangent of phi, this angle phi, is the slope of this curve at that point. And it's also equal to the instantaneous velocity. Other questions? Now let's go over to acceleration. We will basically repeat our definitions. So what we had, we were studying the position, and to describe the changes in the position of the object, we defined this concept of the velocity. Now we know the velocity. The velocity of an object can also change. So to describe the changes in the velocity, we will define this concept of acceleration. So basically, acceleration is nothing but the change in velocity per unit time. Now always keep in mind the similarities between the relationship between position and velocity and the relationship between velocity and acceleration. Now the average velocity we had defined as the change in the position, the displacement, divided by the duration of that change. How long did it take for this change to be realized? Now we define the average acceleration to be the change in the velocity divided by the time it took for that change to come about. Similarly, the instantaneous velocity we had defined as the limit as delta t goes to 0 of delta x over delta t. The instantaneous acceleration, which we will say, we will just denote by A, we won't write this instantaneous. And this is limit of as delta t goes to 0 of delta v over delta t. And A is nothing but dv by dt. Just like the velocity was nothing but the derivative of the position as a function of time, the instantaneous acceleration is nothing but the derivative of the velocity as a function of time. Now we can again give a geometrical interpretation of all of this. So let's assume that we know how the velocity changes as a function of time. So we can make the measurements, so we know the velocity at each instant. So let's just assume that it has such a shape. So let's take 2.2 times t0 and t1. Let's connect those two. And again we form this. Our triangle, right triangle. So this is v1, this is v0. v0 is the velocity at time t0, and v1 is the velocity at time t1. This length over here is v0 minus v1. And this length over here, this other side of this triangle, is t1 minus t0. Now if you want to write down the tangent of that angle, so let's say we had defined the average velocity between time t0 and t1 as v1 minus v0 divided by t1 minus t0, which is, okay, v minus, let's say, v0 minus v1 divided by t0 minus, so, yes, t1 minus t0. Now, this ratio is nothing but tangent of that angle over there. Now, why do I have that minus sign? Before, when we were discussing the velocity, we didn't have such a minus sign. It was just the average was tangent of theta.
Shows the direction.
But why didn't we have such a sign that showed us the direction in the previous expression? You see, I was just saying that we should always keep the analogy between the relationship between position and velocity, and velocity and acceleration. Here there is no minus sign.
Slope is positive, slope there was negative. Sorry. Slope is positive, slope there was negative, so we have to use the minus sign.
Now, one of our aims is to find some definition that will be valid at all times, whether it is moving in the positive direction or in the negative direction.
We took another angle.
Now, when we define the slope of a line, the angle that we should consider is always the angle that the line makes with the positive axis. So if we are looking at the slope of this line, if you draw the horizontal, let's say from here at this point we can define this angle, or even this angle, by the way. So we should always be talking about the angles with this line over here. So you can take either this one. This is usually what is taken, pi minus theta. And tangent of theta is minus tangent of pi minus theta. So again, the slope of this line is tangent of pi minus theta. That is the definition of the slope also. So although here it just turned out to be that there is this minus sign, the average velocity is always equal to the slope of this line. But of course you have to maybe be careful about your definition. How do you define the slope? The slope is not just tangent of an arbitrary angle. It is the angle that your line makes with this line in that direction. So it is this angle over here. That is how you define the slope.
Why did you change the position of the velocities but not the time? In your second equation, minus v0 minus v1?
Well, because here this is v0 minus v1 is the positive number. And that is the length of this side. And t1 minus t0 is the length of this line. Because in the sketch, at least, I'm assuming that t1 is larger than t0 and v0 is larger than v1. So these are just positive lengths. I just wanted to write this expression in terms of the length appearing in that triangle. So if you say that the average, this is acceleration. If you say that the average acceleration is equal to tangent of the slope of this line, that is always true, independent of the direction of the acceleration, whether the acceleration is positive or negative, it is always equal to the tangent of the slope. But of course you have to be careful about what do you mean by slope. Of course, the next thing we can define is the instantaneous acceleration. So if this is our velocity as a function of time curve, now the instantaneous acceleration we had defined as the limit of the change in the velocity divided by the time it takes for that change, as that time goes to zero. So again, what we are actually doing is we are measuring the velocity at a given time, and if we want to find the instantaneous acceleration at that time, we just measure the velocity again right after the first measurement, ideally without giving any time interval. And the velocity will be changing by a very small amount. This delta v will be very small, but delta t will be very small also. So in this limit, it will be a 0 over 0. But nevertheless, the limit will have a finite value. So this is let's say your first measurement. You want to find the acceleration at this time, t0, let's say. So what you do is you make two measurements. Now, whenever you want to measure the acceleration, you have to make two measurements to determine this change in the velocity. So this is your first measurement. You determine the velocity at that time. And then you just make another measurement right after t0. This is your velocity v1. And eventually you move this t1. That's what you want to do. You want this separation between t0 and t1 as small as possible. And if you move that t1 time to t0, what happens is this point moves towards this point. So if you draw a line that connects these 2 points, that line in this limit will just cross our curve only at a single point, and that is the tangent. So if you draw the tangent at this point, let's say this is our angle phi, this is equal to tangent of phi. And this is what we mean by acceleration. Again, it can be positive and negative. In this case, the acceleration is positive because the velocity is increasing. Is it true that the acceleration is positive when the velocity is increasing? Yes or no? So let's vote. So these are the numbers. So this is the question. We are in one dimension. The velocity of an object is increasing. Does that mean that the acceleration is positive? Now, once you vote, you can just discuss with your neighbor and make sure that they also have the same answer. If not, try to convince them. Well, I will stop it over here, and I will ask you one more question. It will be quite related to this one, and after that we can discuss. Okay, of course, when you are reading this, I forgot to write, if the speed is increasing in 1D, the acceleration is always positive. Okay, ask it after we discuss the answer to these questions. Okay, so who wants to explain their answer?
I said A to first and B to second because the speed doesn't have a direction. When we think about speed, we always have to think on the positive side of the graphic. If we take the slope of a let's think about a velocity graph. It can go like this.
Yeah, actually, just A. The speed is always A plus A. It doesn't matter if it's minus A or plus A. For example, it can be plus 10 or minus 10. But we know speed is, for example, when we start speed 0 and A, 2A, 3A, speed is always going like this. It doesn't matter if acceleration is positive or negative, speed is always increasing.
Okay. So you are saying that if the acceleration is constant, speed will be always increasing independent of whether, of course, assuming we start from rest. If the acceleration is non-zero, the speed will always be increasing independent of the sign of the acceleration.
Minus acceleration minus decreasing speed, I guess.
Yes? Okay, so let's make an example. Let's put in some numbers. Let's just imagine that we have two objects. The object 1, its initial velocity, let's say, is minus 3 meters per second. The final velocity is minus 5 meters per second. And our object 2, the initial velocity is minus 5 meters per second. The final velocity is minus 3 meters per second. So what is the initial speed of this object 1? S initial will be just 3 meters per second because this is nothing but the absolute value of the velocity. What is the final speed of the object? 5 meters per second. Again, this is nothing but the absolute value of the final velocity. Now let's say that this happened in a time interval t final minus t initial is equal to 2 seconds. Within 2 seconds, the velocity of this object changed from minus 3 meters per second to minus 5 meters per second. So what is the average acceleration? So it is minus 5 meters per second minus 3 meters per second divided by 2 seconds, so which is minus 2 meters per second squared. So it has a negative acceleration. Although the speed is increasing, you see the speed went from 3 meters per second to 5 meters per second. Minus 1. Yes. Although the speed was increasing, okay, so you see, is the velocity increasing or decreasing? You see, the velocity has this sign. Minus 5 is smaller than minus 3. So velocity is decreasing, whereas the speed is increasing. Since velocity is decreasing, the acceleration is negative. If the velocity was increasing, let's look at this example. In this case, minus 3 is larger than minus 5. The initial speed, well, let's look at the acceleration. What's the average acceleration? Minus 3 meters per second minus 5 meters per second divided by 2 seconds. This is 1 meters per second squared. So velocity is increasing and hence the acceleration is positive. What about the speed? The initial speed will be 5 meters per second. The final speed will be just 3 meters per second, that its speed is decreasing, nevertheless its velocity is increasing. But of course, since the velocity in this case is negative, it's approaching to zero. That is why the speed is decreasing. Now, the definition of the acceleration and the velocity, we can always, for every object, you can define the velocity, you can define the acceleration. And you define the acceleration in terms of the velocities, but you can always talk about the speed also. So these quantities you can always talk about. The acceleration can be zero or non-zero, but it will still be, you can define it, you can calculate it or measure it. Did I answer your question also? Now, any last questions before we give a break? Okay, see you after 10 minutes.
Buyur.